Good morning, everyone, and welcome to today's GoFly Master Lecture. As you know, GoFly is sponsored by Boeing, and we're also joined by a recently announced corporate sponsor, Pratt & Whitney, who's sponsoring the Disruptive Innovation Prize. And there are also a number of in-kind sponsors that are supporting the GoFly Prize. Additionally, we have a number of aviation and engineering organizational partners. This morning, we're happy to welcome Dr. Inderjit Chopra. Dr. Chopra received his Sc.D. in Aero and Astro from MIT in 1977 and joined NASA Ames Stanford University Joint Institute of Aeronautics and Acoustics before joining the University of Maryland as a faculty member in 1981. He has worked on various fundamental problems related to aeromechanics of helicopters, including aeroelastic stability, active vibration control, composite blades, rotor head health monitoring, aeroelastic optimization, smart structures, micro-air vehicles, and comprehensive aeromechanic analyses. He's been the principal investigator of 6 major research programs, served as associate editor of major journals like the International Journal of Micro-Air Vehicle, and has been a part of the advisory board of 5 different journals. Dr. Chopra earned a number of prestigious awards, including the 2012 AHS Igor Sikorsky International Trophy and 2016 ASME Spirit of St. Louis Aviation Medal. He's been a member of the Army Science Board, NASA NRC Aeronautics and Space Engineering Board, and NASA NRC Research and Technology Roundtable Board. He's a fellow of AIAA, fellow of AHS, fellow of ASME, and fellow of Aero Society of India, and an honorary fellow of AHS. We're so excited to be joined this morning by Dr. Chopra. So Dr. Chopra, I'll turn it over to you now for your presentation.
Okay, share. Do you see it?
Yes, I see the slides. You're all set. You can hop right in.
Okay. So my talk is going to be small UAS and delivery drones, challenges and opportunities. So I'm from the University of Maryland, and I've been working in this here for the last 20 years or so. So let me first start with the definition what I'm going to talk about, small UAS. As you know, Department of Defense has divided these unmanned aircraft system into 5 groups. I'm going to talk about group 1, which is at the bottom, called micro mini tactical aircraft. And what is the differential is that the gross weight is less than 20 pounds. Some of the vehicle you see on the top fall under this category. Okay. Micro air vehicles, I think DARPA came up with, under this group, very, very small vehicle definitions, micro air vehicles in 1997, which means no dimension exceed 15 centimeter, gross weight of less than 100 grams. A few years later, they came up with another subcategory, nano air vehicles, which is no dimension exceed 3 inches and gross weight of less than 25 grams. There is another category, very, very small vehicle, pico air vehicles with the dimension of 1 or 2 centimeter, gross weight of less than 10 grams. The delivery drone started very recently. To give you an example, say if the payload is 5 pounds, it covered almost like 86% of packages being delivered by Amazon within a radius of 10 miles, with the endurance, of course, required less than 60 minutes. So both Google and Amazon have been working very feverishly to develop such vehicle. Google came up with the tail sitter with the wingspan about 5 feet with the 4 propellers. Amazon has been working on Cyclo Capture, which is about 8 rotors. They also have some of their derivatives, which you see on this page. Beside these two companies, there are many other companies working on, like DHL, it's a parcel drone. And for example, the bottom right, you see the Domino's also working for pizza delivery. Okay. So let me talk about technology development cycle of 20 years. In 80, started with the PC and Macs. Then 1990, nano and small materials. In 2000 was the beginning of this mobile phone or iPhone. And at the same time was small UAS. And so I think hopefully by 2020, the technology will be more in mature state. Okay. So what are the key drivers of microelectronics? You see miniaturized sensors, servos, and autopilot available. Microprocessing, both the IT and transmission power growing. And this is very closely tied to mobile technology. Advances in microfabrication and 3D printing, numerous potential defense and civil applications, and the low-cost system. Advantage, as you can see, is a compact and lightweight, okay? A rapid deployment, real-time data acquisitions, low radar cross-section, especially very important from military point of view, high maneuverability, and low-cost system. While you see these advantages, there are also disadvantages one has to keep in mind. Safety concern, say collision with other flying object or can cause even personal injury to people. Potential for weaponizing, it can be both positive as well as negative. Security threat, privacy issues, susceptibility to damage, especially if you are flying in a gusty environment or constrained environment, and need to countermeasure against multiple these swarms or collaborative groups. Okay. We'll talk about now potential application of these small unmanned aerial systems. From DoD point of view, small unit building search, small unit cave or demolished building search. All these things started almost like 15 years ago when the start of Afghanistan war. Autonomous small unit perimeter defense, and like over the hill, around the corner, reconnaissance mission. Each one bring their own challenges, and one has to take into account. Another operation in D3, which is a dull, dangerous, dirty environments. Okay. And you can see indoor, outdoor navigation and mapping. Okay. Civil application, the numerous drug delivery in remote places is already going on in some of the African and Asian countries. Videography and photography, especially in parties. Fire rescue operation, this is a new one getting more and more widely used now. Traffic monitoring. Agriculture application, this is a very growing rapidly. Crop spraying, crop estimation, agriculture mapping, crop health monitoring. Okay. I think civil aviation, initially, of course, there is a danger can crash into airplane. So civil aviation people didn't like initially, but now they're also using inspection of airliner is being done in UK. Scanning a runway for debris using high resolution cameras. At the bottom, drones for scaring birds at Edmonton Airport, which is in Canada. And here is what you see here. The big bird is actually drone and produce all sorts of noise to scare birds. This is called a sonic bird repeller. Other civil application, infrastructure inspection, bridges, wind turbine, high voltage cables, gas pipelines, paving lots and roads. I think it's wind turbine, for example, it can take almost like a half a day, if especially off seashore, which can be done in less than an hour. Detection of hazard agents, and also at the bottom security, tagging and targeting, it was also done in Afghanistan. Border law enforcement, counter drug operation, hostage rescue operation. Okay. It's another one, asset mapping is being done. Okay. This is hurricane relief surveillance, was done by Red Cross in Houston area last year. So you heard a wide range of applications. Let me say the capability of a small UAS platform. It's a mobility, intelligence, and multiplicity. For example, the mobility, the smaller, the better. But the gust sensitivity, smaller is terrible. Frequency of operation is much higher in a small, so one has to keep in mind when choosing a sensor. Now here is, of course, perspective of scale. The vertical axis is mass, horizontal axis is the wingspan of the rotor diameter. As you can see, the bluish, the big full-scale rotorcraft, and then the red one is UAVs, the black one birds, and then green is insects, and magenta is rotary seeds. So you can have all these things can fall on actually a trend line. Okay. So small UAS can fall at somewhere large insect and small bird. So what are the challenges? Of course, one is very important, is size, weight, and power constraint, which can be quite critical for sensing and processing. Low radar number aerodynamics, susceptibility to gust, disturbance of the order of capability, small scale, sustained power generation and storage, and operate in obstacle-rich environment which are not even mapped. Okay. How big is the volume? Of course, in the last year, or this year, is 13 million of these platforms has been sold. Platforms which are less than kilogram. Yeah. As you can see, the bottom one is the grayish is the defense, which is more or less saturated, not much change. And the top one is hobbyist, which is again saturated. So the real change is happening is in the civil application, commercial, which is a light pink. In terms of dollar values, currently is about 15 billion and expected to be 25 billion by 2020. This does not cover the delivery drones, which may almost triple this market. Just to give you a feel about delivery drone is a few years we had a AHS student design competition. Our student participated. This is to have a delivery drone in the area of Washington, Baltimore suburbs. It requires a 2-hour delivery, almost like 5,000 packages per day. Okay, in something like a 50 miles by 50 miles. Any peak time at almost need about 443 packages, which means 300 vehicles in the air at a time. So you need, of course, a central warehouse, the customers, drones, and communication. And this is how it will go. So you can see many, almost like 300 vehicles can be at a peak time. So again, started with, I said, DARPA came up with the idea of 100 grams, 60 minutes. Where do we stand today? The fixed wing can achieve that goal, but the rotary wing, they are still struggling around close to about 20 minutes. Okay, they do not have the needed endurance, or the payload. Okay. So I will talk about some of these vehicles later. So what is the required capability? Of course, you need a flight, hover, forward flight, gust hours, and autonomy. Okay. I think you need a feedback control, fast, computationally simple, and robust. Okay. If you think about a quadrotor, you do need a rotor, which means they be exposed in very low random number aerodynamics, propulsion system, motors, speed controllers, sensors, navigation, airframe, and the payload. So let me start some of these elements one by one before coming to a complete system. So low random number aerodynamics, okay, is Rayner number is a viscous force over inertial force. In the full-scale helicopter, the Rayner number can be million or more, whereas small scale can be 10,000 to 100,000. So this is a range where basically the flow from laminar flow to transition to turbulent flow. So laminar flow, where most of these vehicles operate, viscous forces dominate, which are more vulnerable to separation, to adverse pressure gradient, which means CL max, CD minimum, or CL over CD are function of Rayner number, and they get affected. Here is when you look into maximum sectional lift over drag ratio, CL over CD, versus Rayner number. As you can see, with the very smooth flow, I mean, it's very high Rayner number, it's a million and above. Okay, you have a very large CL over CD, but the place where these small vehicles operate, there is a drop, which means low efficiency, and also the test data is also very limited. Low Rayner, first we start with very high Rayner number. As you can see, there is a laminar separation bulb near the leading edge, okay, which get reattached, okay. And as you lower the Rayner number, this separation region spreads. But when you go to very low Rayner number, like 10,000 or around that, there is a separation right near the trailing edge. And that separation region spreads with increasing angle of attack. Okay. So low Rayner number flows prone to complete separation on the top surface. Let's look at just two examples, very simple example. Take a aerofoil on the top. When the blue one is with what the regular system is, the flow coming from the leading edge to the trailing edge. If we reverse the flow, what happens at a low Rayner number? As you can see at the bottom, the lift coefficients versus angle of attack, you almost get almost 30–40% more lift in the reverse flow. Okay. And again, it's because of the separation near the trailing edge for a conventional aerofoil. Okay. So decreasing leading edge bluntness improves low Rayner number performance. Here is an example of, I consider 4 different aerofoils. Okay. 6% camber on the top, trailing edge, just a flat plate, Clark Y aerofoil, and NASA 0012 aerofoil. So I have to say that Clark Y is very often used for propellers. NASA NACA 0012 is used very common in helicopters. At low Rayner number, the CL over CD, which is the polar lift drag polar, I think is CL is the cambered aerofoil is far superior than other aerofoils. As the Rayner number is increased, you will see at very high Rayner number, the aerofoil, the smooth aerofoil is much better than flat plate or basically even a camber plane. So it tells you the thin cambered aerofoil perform best for small UAS scales. Another one, I take even a steady flow in a flat plate and steady flow, a real number of 10,000, 100,000, and a million. Okay, 10,000, there is a lot of oscillatory flow, okay, which is not the case at a high real number. As you can see, the flow on the very first 10,000, 10 raised to power 4, there is a lot of vortices which are being shed. Okay. If you take an oscillatory flow at a low real number, which is what's defined by reduced frequency, K very, very small, 0.005 is like a quasi-steady, 0.05 is an unsteady, and 0.5 is a highly unsteady. Okay, and as you can see, as the reduced frequency decreases, increased presence of high frequency content. Okay. So let's see, low real number 4 are very susceptible to separation. Aerofoil characteristic like lift, drag, moment are nonlinear and sensitive to real number at low real number. Okay. So we need minimum thickness, moderate camber, and sharp leading edge for low real number aerofoils. Okay. So the future recommendation is CFD modeling require refined transition and turbulence model. Can need detailed experiments, including pressure distribution and PI measurement for steady and non-steady flow to validate your analysis, CFD analysis. Coming back to now propulsion, the next topic, okay, electric motor, battery, IC engines, okay. So let's start with the brushed motor. In case of brushed motor, okay, magnets are stationary, the coil is rotating, and the brush is, of course, wear with the time. Simple design, brush friction, appropriate for UAS which are less than 100 grams. Brushless, the magnets are rotating and then they coil, and then because of you need a phase voltage to the coils, and speed controller becomes much more important. As a result, it's heavier, and it's probably important for vehicles which are more than 100 grams. Also, you're looking into efficiency, vertical axis efficiency, and as you can see, the maximum efficiency in a narrow range of power output, good for direct drive, high RPM, and low torque. Brushless, maximum efficiency in a wide range of power output, which means gentle drop, keep throttle 100% and vary voltage for maximum efficiency. Okay. If you look at overall efficiency versus weight, we have both brushed and brushless motors in this one. The maximum operating efficiency decreases as size decreases. Okay. So one has to choose the motor appropriately for one's mission. Conclusion, brushless and brushed DC motors are choice of small vehicles. Brushed for less than 100 grams, brushless for more than 100 grams. Efficiency decreases with the lower size. A good recommendation for future is one need to examine these electromechanical parameters for small size motors. It's not available, readily available. Okay. Develop efficient speed control. That's where one need to spend a lot more energy and time. Going back to batteries, a lot of people think the battery, not much research in that area. It's a tremendous amount of research going on. Okay. No doubt, lithium-ion battery is probably the most energy system. Energy density is energy stored per unit volume. Specific energy is the energy stored overweight of the battery. During the last 15 years, there has been 8% yearly battery capacity increase. That is all because of the cell technology. What's happening is specific energy going up, price going down, life of batteries going up, recharge time going down, and batteries become more flexible. Okay. Internal combustion engines at a small scale. Okay. Specific energy hydrocarbon fuel is about 100 times of electrochemical materials. It can be mass produced and very cheap. However, when the efficiency, you look at a small weight, okay, or small displacement is going down tremendously. It can be also like a single-digit efficiency because of increased losses with heat transfer, fluid friction, and leakage with the small size. Performance efficiency falls rapidly with miniature. Not possible to maintain adequate thermal isolation between a hot and cold side. There is an enormous potential to develop miniaturized IC engines. One has to use material with high thermal isolation, increase combustion efficiency, and also one has to be very careful in terms of acoustics, because these can be very, very noisy also. Okay. Microfabrication 3D printing, there has been tremendous progress in this area. 3D printing suited for small batch parts, rapid prototyping, and additive manufacturing. Saving of material because you don't layer-wise. Adaptation from CAD. And material can be both polymers and metals. Numerous parts are built using 3D printing today. The major concern is consistency of material properties over batches and time. And again, a lot of research going on in this direction now. Microelectronics, I'm going to talk about the lidars, radars, GPS, and so on and so forth. If you look into autonomous UAV system, you need a flight control hardware, you need a navigational sensors, you need communications, and also because you are working in an obstacle-rich environment, situational awareness, and most important, of course, is a processor, which is the computer. What are the attributes needed, which is a compact, lightweight, low power requirement, low processing requirement, and need to be robust and cheap. Coming back to difference between lidar and radar. And radar uses pulse laser light to measure and detect distance of object. Okay. High resolution can detect small objects and sense nearby objects. On the radar uses radio waves, okay, measure velocity of object. Lower resolution suitable for larger object, can sense velocity, direction, and distance of faraway objects. Okay. And here is an example of lidars. A lot of research going on because of autonomous cars. Here is on the left side with the yellow. The lidar is basically 75 grams, and it can be used for collision avoidance. Ultrasonic sensor measure distance using bouncing back of sound wave of specific frequency from an object. It can be very light, say something like 4 grams, and very inexpensive. It's not affected by color, dust, dirt, can be used in dark even, low cost. Accuracy depends on temperature, reflective material, but it's always a small distance. Okay. Cameras, I think after the invention of digital camera, there have been tremendous progress in cameras. And now with the cell phone, even more progress. Two types of cameras, CCD and CMO. As CCD, low noise images is more accurate, but also expensive. With the CCD, the CMOs, widely available, cheap, okay, compact. And again, there have been a market driver for image processing. It's the cell phone. Needs smaller, lighter, and sharp imaging. And there's a lot of progress going on in CMOs. Okay. An optic flow sensor is basically, again, using these cameras, you can get optic flow pattern to apparent motion of object. It's a relative motion between object and the scene. So, computer vision. Computer can achieve understanding from digital images or videos. Involves acquiring, processing, and understanding of digital imaging. It needs a lot of processing power. And only very recently, now iPhone 10 has used this computer vision to identify the owner. I think, imagine in the future, you don't need any lock. And if basically computer vision can find out who the owner is. Okay. So let me talk about now microprocessor, which is basically a computer. To give you example of iPhone itself. See your iPhone 4S and iPhone 8, which was last year. The top line, dotted line is a calibration Intel code for desktop computer, which is the baseline. So iPhone 8 has a processor which is a more powerful than this basically tabletop computer. So coming back again, embedded, lightweight, of course, we're talking about autopilot, which also have IMU, okay? So, which has a processor. The sensor, in terms of sensor, you need an integrated 3-axis gyroscope, 3-axis accelerometer, and 3-axis magnetometer. And now giving you example, what we have today, like this ALCA, which is what have a autopilot. With all these things, it can have actually actuator support, can up to 12 actuator. And the total weight is 1.6 gram, less than a 1-inch scale. Snapdragon Flight, which is another one, has come out very recently from Qualcomm. Okay, it is about 26 gram, very powerful computer. In addition, it also has basically a camera with this, 2 cameras with this. Okay, and a language it uses Linux, so you can basically, it's an integrated platform, or the whole thing is on a chip. Coming back to the navigation, location, GPS and cell tower. So let me say a few words about GPS. GPS is operated by US Air Force. Okay, used to be 24 satellite and now 32 satellite in operation all the time. And you basically, when you GPS, when you connect with at least 6 satellite, and it tells you basically try to give you the locations and the time. Of course, with the cell tower, you have where antenna and electronics communication equipments are placed. So light of sight. So inside operating with the satellite, you can get your internet using these cell tower. So most of the cell computers are connected with the cell tower. In a flat land, it can go almost 30 to 45 miles, whereas in hilly areas, you need to be more cell towers. Okay. Just to talk about GPS, how big it is today. The GPS on your cell computer is less than about 5 grams. It is expected to have a spatial resolution of less than a foot now. Autonomy, what you have is when you go into high level, bigger size, there is a lot more autonomy. The smaller size, The autonomy is slowly growing as the computer, the processor are becoming faster, miniaturized, and also the sensors are becoming lightweight. Okay, so I'm slowly, I think with the small vehicles, the autonomy level will grow. Here is an example. Of course, this is using Vicon system. Another example is this is using a gas cards. It's trying to get it back inside the vehicle. Okay, coming back to integrated vehicles. Okay, if it's a non-hovering vehicle, then the fixed wing is the way to go. Hovering vehicle can be single main rotor, coaxial rotor, shrouded rotor, quadrotor, or it can be unconventional rotor-based design. Long-range endurance compound can be tilt rotor, tilt wing, or tail sitter. Hovering or non-hovering also can be flapping wing. If it's an insect base, then it can hover. If it's avian base, means a long distance. Also can be reaction base, which are very power intensive. We don't talk about those. Rotor base, there are two most important factors: figure of merit, which means ideal power required to hover, actual power required to hover. Power loading, thrust produced per unit power. Okay. Here is the power loading on the vertical axis, and it's very much function of disk loading, which is a load per unit area of the rotor disk. Okay. As you can see, the birds, the insects, they are much more efficient, and so are some other vehicles. Okay, because you need to have a very low disk loading. Where do we stand? Figure of merit. For full scale, you have 0.7 to 0.85, whereas MSB scale is low because of a lot of parasite drag. Power loading is the other way. Okay, that's because the disk loading is very, very small at small vehicles. So when I look into the hover power, as you see green, it consists of two components: profile power and the induced power. And it is in case of full scale, the induced power, the profile power over induced power is a 10 to 15%, which is not the case with the MAV. And the reason is profile power is 5 to 8 times because of the aerofoils, a lot of drag. Induced power also is very large at a small scale. And as you see on the figure right-hand side, on the top, there is a lot of separation, all sorts of vortices in a small scale. Single main rotor. Of course, if I take a single motor, there are a whole range of vehicles available. 18 gram is the most prox dynamics, and I'll talk with a little bit about that one. It's about 18 gram gross weight, rotor diameter of 12 centimeter. Okay, it can go almost like a 25 minutes. Okay, it has also GPS and a camera and a digital link, and so it comes as a kit as a 2-copter in 1.3 kilogram. You cannot buy it; it's only defense related, and also very expensive, of $350,000 for this kit. Okay. So what do we need to? We need to improve small rotor hover efficiency. Okay. So where we are, if I look into this is induced power over, say, profile power. This is where we are right now, very low figure of merit. This is a full scale. There is a long way to go there, which means the aerofoil efficiency need to be improved. Induced losses need to be reduced. Okay. So we did a whole lot of, for example, if you take a rotor with the, say, rotor diameter of 3 inch. Okay. Tried many different aerofoil shapes. Card, variation of card, variation number of blades, effect of twist, okay, and effect of planform, also effect of winglets at the tip. Okay, but something like 500 rotor design tested, and come back to the conclusion. We have a two-bladed, 6% cambered, tin plate of 2% thickness, and modest twist. Okay, as you can see here, the figure of merit is close to 0.67, and you can also validate with the CFD analysis. Okay, so this is the highest figure of merit ever reported at a small scale. Coaxial rotor, there are quite a few in a range of weights. Okay, and at least if one put a lot of attention to the design, you can certainly improve, as is shown in this graph. Instead of having a hover endurance of 3 minutes for the same power, you can get almost like 20 minutes. So coaxial rotor is a compact design. And of course, the mechanical complexity of design, poor yaw stability, aerodynamic efficiency is low and needs significant rotor separation at high speed, which means more drag. A single main rotor with anti-torque vane, which means the no-tail rotor. These vanes at the bottom are exposed to the flow of the main rotor. Okay. Again, one has to go through very carefully, and then we find one need basically is some sort of a shroud to see the wake. Okay. To keep the wake on the compact and simple design. These are the advantages that you don't need a tail rotor. Flight stability issue near ground, limited control authority, needed additional power because of hub and wings, almost like the same level as tail rotor. Shrouded rotor, being used very widely in tail rotor of full scale. Okay. Try to see at a small scale whether we can also use a shroud. A shroud has to be very lightweight. The key factor, of course, keep in mind that the rotor tip has to be very close to the shroud so that you can weaken the tip vortex. The lip radius has to be modest, say 13% of the rotor. Diffuser angle modest, okay, something like 10 degree. And the length of the shroud is also very important. Let's say it's a 3/4 of the radius. You can almost double the thrust for the same power. The challenges is, of course, the structural weight of shroud, and also the performance degrade in the forward flight. The two factor, of course, not only you get a lot of drag, but also got a very large pitching moment with the sideways flow. Very sensitive to gust. Pros, of course, shroud protects rotor, which is very important. Improved hover efficiency, delay stall. Of course, it's challenging of design shroud, has to be lightweight but stiff. Okay, and degrading forward flight performance. Okay, high pitching moment in forward flight and more susceptible to gust. So it's another example. Yeah, one can certainly see these. Okay. Quadrotor, most popular right now, and there are a whole range of quadrotor available. Okay, and of course, if you look into, these are some of the key factors: rotors, batteries, motors, airframe. And if you look at it, there is no consistency in weight of available quadrotor, because many of these things have been iteratively built, and there are no available design to build these things. Okay, so if we look very carefully. Here is something like a 45 grams quadrotor. That's a gross weight. Okay, and we went through very carefully in terms of designing such a system. Okay, and we basically brought down from almost like 7 or 8 minutes of time, hour time, to 30 minutes of time. Okay, and also is of course very, very much more efficient. So what you see is the optimized quadrotor also have a much higher performance, almost like 0.7 figure of merit. So pros is a mechanical simple quadrotor as a whole. You don't need a tail rotor. Flight dynamics simple because you can be RPM control. Larger CG travel possible. Cons is of course multi-rotor, which means more susceptibility to failure because there are more rotating components. Airframe drag and forward flight can be an issue. Okay. So overall rotor blades challenges is improve hover figure of merit from 0.7 to 0.5, the current one to 0.75. Increase range, endurance payload based on specific flight mission. Improve susceptibility to gust. This is a very big issue for small rotor. Optimize propulsions. Okay. So looking into unconventional rotor blade configuration, I give you one example, Cyclo Capture. Okay. As you can see, the rotor is in the axial direction. Blade pitch changes periodically as it rotates. At the top and the bottom both has to be in the positive direction. Okay. The environment more or less more identical in the spanwise direction. Okay. The idea of this cyclocopter was more than 100-year-old. Many people tried, including Boeing, but they did not have good success because they tried to build a big one and the design tools were not available, understanding was very limited. And this idea, and almost like 75 or a year later, people again started looking at carefully. And we at Maryland gone through very systematically, okay, to see the idea. Why are we looking at this one? If you look at the disk loading at the bottom and the power loading on the top, okay, if we take a optimize this cyclider rotor and optimize conventional rotor, then you have much more efficiency because of many unsteady forces. So we built a range of these vehicles, a quad cyclocopter 800 gram and also 50 grams, a twin. Okay. And the blue one, the triangles are basically the efficiency. It's much more efficient than conventional rotors. As you can see here, you can have a thrust vector because the angle at the top and the bottom are positive. You can tilt the thrust vector in any direction, so you can have almost like 360 degree of tilt. So which means very maneuverable, okay, which means cost tolerant. So seamless from hover to high speed forward flight. This is and as you can see, the power required in forward speed, 11 meters per second is very high in small scale. You also had 40% of our power. Okay. So you can get high speed very efficiently. And it doesn't take the best of anything. This is a micro cyclocopter built by Texas A&M, 29 grams. And again, this is a small cyclocopter. All-terrain cyclocopter, Right? You can see there. It's a quad Cyclo Capture, which can not only move on the ground, but also can hover. And also can on the water. Okay. Power loading, better Cyclo Capture conclusion, better than a conventional rotor. Absence of blade stall pitching, amplitude something like 45 degree. Require 12% of hour power in terrestrial mode, which means on the ground. 8% of hour power in aquatic mode on water. Development of high-speed, gust-tolerant, autonomous Cyclo Capture. Okay. Aerodynamic efficient at small scale. You can have thrust vector capability. Highly maneuverable, which means very gust tolerant. Tons of mechanical complexity, pitch change, airframe drag, and forward flight. So, coming back to if you want to get into very specific mission, achieve a high-speed flight mission with vertical takeoff and landing. Rotorcraft is good in hour efficiency. Fixed wing good for cruise efficiency. So have basically some sort of a compound, tail sitter, tilt rotor, tilt wing. Of course, the major challenge is the transition flight, helicopter to fixed wing and fixed wing to hover. So here is the 230 grams of quad rotor biplane. So quad rotor is very popular. You can using a wing, you can get a biplane. And what's happening is you can require almost 1/3 of hour power for forward speed. Okay, so here is a good example of our forward flight. And here will be the actual example, which can be very efficiently used for that. Pros, adaptable from widely popular quadrotor, simple design without control surfaces, scalable concept, compromise performance, non-ideal pitch setting, more sensitive to gust. Okay. So overall conclusion of the rotor base is conventional rotor, single rotor coaxial quad, design principle for simple mission very mature, susceptibility to gust, limited forward speed. Okay. The second, the gust stall is a very problem. Unconventional rotor Cyclo Capture design principle for hover very acceptable, more maneuverability or better tolerance to gust, potential for superior forward flight. Okay. Compound rotor design principle adequate, challenges transition mechanism from hover to forward flight, again susceptible to gust, but high speed possibility, so one can get more range and endurance. Future research is design the vehicle for a specific mission. Based on the mission, you can come up with the right type of vehicles. Flapping wing based, of course, you have both insect and rotor. As far as the avian is concerned, they're flapping in vertical plane, moderate variation of wing pitch, twist down on downstroke, twisted up on upstroke, but the isomorphing of the wing also takes place. Whereas in insect, flapping in a horizontal plane, large variation in wing pitch, hover capable. The avian are not hover capable. Also see the radar number in the insect is very low. Avian is high. The frequency range is also very different, much high in insect than avian. Okay, so good gust tolerance with the insect base, it can hover. Okay, but the design is quite complex. What is where the vehicles available? Many attempts have been made. okay? But most of the vehicles have very, very low endurance. The limited success, the most successful is a Hummingbird by Aero Environment. It has endurance of 4 minutes. The other one I will say, based by Texas A&M with endurance of 1 minute. Flapping wing in a similar stage, very limited design. Okay, just to looking into the different wing motions, you have upstroke, downstroke at very high pitch angle, pronation and supination when the wing tilt from one direction to other. The key parameter is wing frequency, flap amplitude, pitch angle, and also the flexibility of the wing, which is what we call aeroelastic couplings. Okay. So I said has to be unsteady wing motion and lightweight wing structure. The wing weight is very important. So Aero Environment went to hundreds of iterations on the wing design to find the right wing. Okay. So what's the problem is a limited understanding of flow physics and expected performance of flight wing in flight. Okay. So here is a large-scale wing being tested in wind tunnel. Okay. So if we take it the PIV measurement of a 1 quarter span, you can very easily predict with the CFD as long as you have a proper CFD validated with experimental data, and you can find out the lift time variation plus as well as the steady lift, plus also the power. You can get a good estimate using CFD tool. Okay, but the overall performance, and just see the right figure of merit with the flapping wing of today is very, very low. Okay. So ultralight wing design with a high frequency and a control implementation. It is a good example of this is being done by the Texas A&M. Okay, so instead of a flapping system, okay, I will say wing kinematic complex, basic principle of flight become more clear. Right design principle very rudimentary, and control integrated vehicles not ready. Avian base, many similar type of issues. Of course, future is people have to really iteratively build these things and then validate with the test data. So coming back to my almost at the conclusion, where were we? The vehicles why 10 years ago, mostly fixed wing, today mostly quadrotor, and the future will be the vehicle will be based on the mission. Payload today is a modest. There was no payload 10 years ago, but I think again, the mission-based payload, what we require in terms of as a sensor. Again, speed, range, low, modest, and higher speed. Navigational, insight, mostly insight today, and will be out of sight in future. Propulsion, battery today. I think maybe future people may have to look into fuel cell and internal combustions, in addition to efficient battery. Flight robustness, low, modest, and need to be high in gusty environment and obstacle-rich environment in the future. Autonomy, none. Semi-autonomous today, full autonomy will be the focus of the future. Okay. So it is, as I said, small delivery drones. It's a multidisciplinary system, require aeromechanics, micropropulsion, microelectronics, and all these things. There are many challenges. Increase in the hover figure of merit, power loading, increase of payload, range, endurance, major increase in autonomy, and a significant increase in flight robustness and integrity. These will be the issues of future. I'd just like to acknowledge many of these young PhD students, faculties, and sponsors. And I probably stop it here. It's a wonderful world of small UAS, and there are many, many future applications and interest. So I started. Thank you.
Thanks so much, Dr. Chopra. We're just here at time, so to finish off for us, do you have a piece of advice that you'd like to give the GoFly community who are thinking about building their personal flying devices? What important piece of advice should they be thinking about?
I think it's the most important thing is to go systematically, methodically, and basically you will come up with a better design. And the second, design is very based on the mission. Okay, it should be mission specific because you cannot have the same design valid for a range of missions because it will not be very efficient. So once you decide your mission, you can come up with the right vehicle and then basically pay attention to what already is available in literature, look at it, and then decide. One piece of advice is learn more about the cell computer. There's a lot more learning about what's going on in cell technology, which can be easily transitioned into your small vehicle.
Great. Thanks so much, Dr. Chopra. I'm sure that all of our attendees here today and everyone who will be watching in the future will very much enjoy your lecture. So thank you so much for joining us today.
Thank you.